Hello, and welcome to this clip going through a slightly older chemistry Olympiad question. This is from the 2001 paper, and it's a rates of reaction initial rates method. It's fairly similar in its layout to most of the initial rates questions that you'll come across on modern A-level papers, so it's worth having a go at to practice your skills on this quite important technique. So looking at the first part of the question, it says bromate 5 ions react with bromide ions in the presence of acid to produce bromine. So in the presence of acid means H plus aqueous is a reactant. And you might not have come across bromate 5, but basically that means it's an ion that contains oxygen and bromine with Br in the plus 5 oxidation state. So essentially, they're giving you all the things that are going to be in the equation, but in words. So you have to process what they've given you in words to turn it into an actual equation. Now, so far, that's what we're able to put. Notice I haven't put a charge on the bromate ion, and I haven't completed the balanced equation yet. Now, you need to use up an oxygen from the bromate, so that must mean that the H plus an oxygen might go together to make water. That would be a good idea to start with. Now, the only way I can put it so that bromine has a plus 5 oxidation state is for 3 oxygens, which would each have -2 to a total -6, for the whole thing to be -1 overall. So now what I need to do is look at balancing it. So first I balance my oxygens by putting in 3 H2Os. That now means I've got 6 H pluses, but I need to balance the charges on the left-hand side. I've only got 2 minuses. So what I now need to do is to put in 5 Br minuses, like that. And obviously that now means that I need to make sure I've got 6 bromines on the right-hand side. So there we go. So obviously at A2 level, you need to make sure that your charges are balanced as well as your species. So the next part, part B, is asking us to calculate partial orders. So in this part, the partial order can be taken to mean the same as order with respect to a specific species. So when you talk about order with respect to bromate 5, order with respect to bromide, order with respect to hydrogen. That's what they're after. And as you'd remember from the textbook, the total order would be the sum of the individual orders. In this case, they're called partial orders. So the key to doing this is to find pairs of experiments where everything else stays the same, but only the one that you're looking at is changing. So you can see that the data is not provided as concentrations like you'd find in normal A-level questions. But if you look at the concentration of each of the reactants, it's 1 mole per decimeter to the -3. It's only the volume that changes. So what we can do instead is use volume instead of concentration in the rate equation. So I've done a slightly different version of the rate equation, still using K, but VA is the volume of A, VB is the volume of B, X and Y are the respective partial orders. So applying this idea to experiments 1 and 3, the volume of bromate doubles from 5 to 10, the volume of bromide stays at 25, and the volume of acid stays at 30. So the order with respect to bromate is 1, because the initial rate doubles from 1.68 times 10 to the -5 moles per decimeter -3 second to the -1 to 3.37. Well, the calculator would suggest you should go to 3.36, but 3.37 is pretty close to doubling the rate. So looking at experiments 1 and 4 for bromide ions, the volume of BrO3 minus would be tripled from 5 to 15. That would increase the rate times 3 to 5.04 times 10 to the minus 5. So the volume of Br minus doubles. So you apply this to 5.04 times 10 to the minus 5 to get 1.008 times 10 to the minus 4, which is the initial rate that we've got in experiment 4. So that means it's first order with respect to Br minus as well. So doing the final one for hydrogen ions, we're looking at the column here which has HX, which is an acid. So the volumes of bromate and Br minus remain unchanged. Both the bromate is at 5 and the Br minus is at 25. But if you look, the volume of H plus increases times 2. It goes from 30 to 60, and the rate increases times 4. So therefore, the order with respect to H plus is 2. So now what they want us to do is to calculate the rate constant for this reaction. So what they want you to do next is to calculate the value of the reaction rate constant for this reaction, including its units. So I've given you the rate equation, which will be easy to construct now that we know that bromate is first order, bromide is first order, and hydrogen ions are second order. So now all we have to do is choose one particular row and insert the values. So I'm going to go for experiment 1. Now we've got the rearrangement to get the value of K. Now the slight problem we have is that rate is in terms of moles per decimeter to the minus 3 second to the minus 1. And in the denominator of that expression, the square brackets mean that all of those values are in concentrations. Now we didn't have to bother with using concentrations before because it was all relative in terms of the volumes, because, like I said, it was the same concentration, but there's different volumes being used. This time round, they've given you a column that tells you the volume of H2O. So this now has to be taken into account. So there's 2 steps we have to do for each of the concentration terms in the denominator, of the expression for K. First of all, we have to work out the moles present, and then we have to work out the concentration using the volume of water used. So for example, in experiment 1, you'll see that there's 40 centimeters cubed of water used, plus there's 5 centimeters cubed of bromate, so the total volume is 45. So just taking the 5 centimeters cubed of 1 mole per decimeter cubed of bromate, that equates to 5 times 10 to the minus 3 moles. So we do the same for our bromide and for our H+. So that gives us 3 values. I'm going to pop those values underneath each concentration term, because we're going to use those for the second half of the calculation in a second. So now we're taking into account the volume of H2O. So to get the concentration, you need to take the number of moles that you have and divide it by the total volume in that particular mixture, in that experiment. So the total volume is, sorry, I beg your pardon, it's not 45, it's everything together, so I'm just going to change that. Now in blue I've put in 100 because 5.0 plus 25 plus 30 plus 40, in fact all of the volumes added up together gives you 100. In terms of decimeters cubed, you have to divide that by 1,000. So the complete calculation gives us 0.05 moles per decimeter to the minus 3. So I've now put that in underneath BrO3 minus. I can do the same thing for bromide and for H+. So you can probably see the pattern that's emerging. We simply take the number of moles and multiply it by 10, because the total volume is 1/10 of a decimeter cubed. So we could now insert the values from the, in terms of concentrations, and also the rate from experiment 1. So the mathematical value that you get is 1.49 times 10 to the minus 2. Now what we've got to do is to work out the units. So combining all the concentration terms together in the denominator, that gives you moles to the 4, decimeter to the minus 12. So by cancelling, you get moles to the minus 3, decimeter to the 9, second to the minus 1 as the units. Okay, so let's now move on to the final part, part D. So it now says calculate the new initial rate if 0.100 mole per decimeter to the minus 3 ethanoic acid has been used instead of the 1.00 mole per decimeter minus 3 of HX in experiment 1. So this requires you to use the weak acid calculation and then put this new number into the calculation we just did. So there's the same complete volume, 100, but the number of moles of H+, and therefore its concentration, are going to be different. So you can probably work out that ethanoic acid is going to dissociate into an ethanoate ion and one H+, so it's a monoprotic or monobasic acid. So that's our Ka expression. Now we don't know what the volume or the number of moles or the concentration of ethanoate ions are, but we can use the old trick of using H+. So we're given the pKa, and if you remember the weak acid calculation, you can use H+ squared. So I've taken one step out of the calculation and just put H+ equals the square root of Ka times the concentration of CH3COOH. Now what we've got to do is find the concentration of CH3COOH. So remembering the same trick we used before, we worked out the moles of our reactant. So the moles of CH3COOH is C times V. So we have 0.1 as our concentration, because the question tells us that. And it's 30 centimeters cubed we've added. So 30 over 1,000, you multiply that by. That gives you 0.003. So now what we can do is put that into the equation at the top. So that gives us 0.03 moles per decimeter to the minus 3. Now that can be now put into the equation for H+. So I'm just going to do that calculation now. So that gives us 7.22 times 10 to the minus 4 moles per decimeter minus 3. So using our values for the concentrations we'd worked out earlier, I'm putting in 0.05 for my bromate, 0.25 for my bromide, and this time I'm putting in 7.22 times 10 to the minus 4 squared. So all of that together, multiplied by K, which was 1.49 times 10 to the minus 2, that gives you 9.71 times 10 to the minus 11 moles per decimeter to the minus 3 seconds to the minus 1. So hopefully this has been an interesting look through a rates question that actually looks a bit easier than it actually is. Once you get into it, you realise, I've got to change my data around a bit. Plus they've got quite a difficult weak acid calculation part of it at the end as well. So until next time, thanks for listening and see you soon.